Welcome to The Explainer. Today, we're going to completely demystify the preparation journey for competitive entrance exams. If you've ever felt totally overwhelmed by the sheer mountain of physics sitting right in front of you, well, you are absolutely in the right place. We're going to start by tackling the psychological hurdles that hold most students back, and then wrap up with the core mathematical secrets you literally need to succeed. Let's get into it.
Okay, so let's kick things off with some pretty stark, almost humorous statistics. When you break down the harsh reality of student prep, you get this massive, glaring chunk of data. A staggering 59% of students enroll in coaching, but, frankly, they don't actually put in the study hours. And the kicker? When asked why they're failing, they jokingly blame it on their past life karma. I mean, it's a funny excuse, sure, but it really highlights a serious lack of accountability. Only about 25% are actually studying with 100% dedication. Our goal? We need to make sure you're in that 25%.
Getting into that top tier, though, requires a really profound shift in attitude. There's this incredibly powerful Hindi quote from our sources that sets the perfect tone here. Translated, it says, "Every bird here is wounded, but the one who could fly again is the only one truly alive." You know, everyone finds exam prep tough. It's an absolute grind, a battle. But your resilience, your ability to just pick yourself up after bombing a mock test or struggling with a brutal concept, that is what ultimately defines your success.
So here's our roadmap for today. We'll start with mindset and common mistakes, map out the actual physics syllabus, and then dive deep into the basic unitary method, calculating uniform change, and finally, density and mass scaling. Part 1. Mindset and mistakes. Fix your strategy.
Before we even touch a physics problem, we absolutely have to fix the foundational errors in our approach. Our sources highlight some incredibly common pitfalls, proving that just taking a drop year or enrolling in some fancy, prestigious batch won't guarantee your selection at all. I mean, spending 3 to 4 months just searching for the perfect teacher or batch, that is a massive waste of time. Or what about skipping a class just because you think you already know the topic? Huge mistake. But the biggest pitfall of the whole shebang? Avoiding practice. You might know the physics concept perfectly in your head, but if you skip the practice, you're going to inevitably fail the actual calculation on exam day.
Students also constantly fall into this really toxic trap. They obsess, wondering, is everything going to be taught to an advanced level, or are we starting from the absolute basics? And this anxiety literally paralyzes them. But the reality? The subject itself doesn't care about these labels. True mastery requires a completely different approach, one that naturally bridges the absolute basics directly to the most advanced applications. Which brings us to Part 2, Syllabus Map, the Physics Battlefield. To resolve that whole basic versus advanced anxiety, we just need to take a step back and look at the actual physics battlefield. And the solution is kind of hiding in plain sight. If you look at a clear 33-chapter syllabus planner, what is chapter number 1? Actually, think about it for a second. It isn't kinematics. It's not Newton's laws. It's mathematical tools. This proves that mastering foundational math isn't just basic prep. It's your essential survival gear. Without this toolkit, conquering the remaining 32 chapters is going to feel pretty much impossible. Moving right along to Part 3, the unitary method, your first essential math tool. Let's explore our first mathematical weapon. This really proves that what we call advanced physics is often just grade school math scaled up. Think of a super simple problem. If 500 rupees buys you 20 mangoes, how many mangoes do you get for 300 rupees? Well, you find the value of one unit, then multiply, right? Super basic. But here's the crazy part. The exact same basic unitary method used to calculate the cost of those mangoes is the exact same math used to find the charge of a 45-degree arc on a uniformly charged ring with a total charge of 120 coulombs over 360 degrees. It is literally the same math. And we can repeatedly apply this exact same logic to the physical world. Take this scenario. You've got a rod of total mass m and total length L suspended from a roof. Now you need to find the mass of a specific segment of length x. Using that unitary method, you simply say, okay, the mass of a unit length is m divided by L, therefore the mass of length x is just that, m over L multiplied by x. It's just simple division and multiplication, instantly solving what looks like a tricky mechanics problem at first glance. All right, Part 4, Uniform Change in Dynamic Systems. Moving from static objects like rods and rings, we run into our next crucial mathematical tool,
The main thing here is really grasping the definition. Uniform change just means there is a constant rate of increase or decrease in a physical quantity over a specific unit, usually time or distance. When a physical property changes uniformly, it means it's completely predictable. We can calculate its exact state at any intermediate point without needing any complex calculus.
Let's see this in action, shall we? Say a car's speed increases uniformly from 10 meters per second up to 70 meters per second over a span of 12 seconds. How fast is it going at exactly the 5-second mark? Well, we simply find the change per second. The total change is 60 over 12 seconds, which gives us 5 meters per second every single second, so over 5 seconds, the speed increases by 25. Add that 25 to our starting speed of 10 and boom, we get exactly 35 meters per second. Easy, right?
Now, what's really fascinating here is how we can take that exact same mathematical logic and apply it to a totally different physics concept, like thermodynamics. Imagine tracking a temperature drop from 175 degrees down to 25 degrees across a 15-meter-long rod. That is a 150-degree change over 15 meters, meaning you have a uniform change of 10 degrees per meter. So if we want to know the temperature 3 meters from the cooler end, we just calculate a 30-degree change, giving us 55 degrees. Speed, temperature, the underlying math of uniform change is completely identical.
And finally, part 5, density and scaling for 3D mass calculations. For our final climactic challenge in this explainer, we're going to scale things up into 3 dimensions. One of the most common high-level exam questions involves objects with cavities scooped right out of them. To solve these complex cavity problems, we follow a very precise, structured strategy. And this entire strategy relies on one fundamental truth. Density only depends on the material, so it stays constant. Because of that, mass scales directly with volume, and for shapes like spheres, volume scales with the cube of the radius. Understanding this geometric scaling is basically a superpower. Think about it. If you have a 10-kilogram sphere with a radius of r, and you're given another sphere of the exact same material but with double the radius, so 2r, the mass doesn't just double. No way, because volume is proportional to the radius cubed. Doubling that radius means the volume multiplies by 2 cubed, which is 8. So just like that, your 10-kilogram sphere becomes a massive 80-kilogram sphere. So let's apply this to tackle an ultimate tier problem from our sources. Imagine a massive 540-kilogram solid sphere. Now, imagine a spherical cavity with a radius exactly 1/3 of the original sphere is just scooped right out from the inside. The big question is, what is the remaining mass of this new hollowed-out shape? Trying to calculate the volume of that awkward remaining shape directly, yeah, that would be an absolute nightmare. But this is exactly where our scaling rule saves the day. Because the cavity's radius is 1/3 of the total radius, its volume, and therefore its mass, is 1/3 cubed. That means the cavity represents 1/27th of the total original mass. And what's 540 divided by 27? It's 20. The scooped out part weighs exactly 20 kilograms. We just subtract that 20 from our original 540, and we find our final answer. The remaining mass is 520 kilograms. It's elegant, it's incredibly fast, and it is entirely built on basic math scaling. Tying this all back to where we started today, I want you to honestly ask yourself something. Is your exam prep strategy built on avoiding practice and throwing around excuses like past life karma? Or are you genuinely ready to buckle down and master the mathematical tools that actually build success? The syllabus isn't some unbeatable mystery. It's just a puzzle. And now, you've got the tools to solve it. So what are you going to do next?